Hi, I'm Leo, and this quarter, my partner Dimitri and I have been working on Notebot. So what Notebot is supposed to do is roam around tables looking for notebooks like this one, and then when it finds a notebook, it's going to stop and light it up. And it does this using computer vision. It has an optical camera that's downward facing, and as a little demo here, if I remove the notebook, it's going to continue to roam. And again, if it finds a notebook, it stops. And what we wanted to differentiate is not recognizing iPads and other such devices. So you can see here I have a laptop, and Notebot is going to continue to roam and not recognize the laptop.
First, we'll talk about some of the hardware challenges we faced during this work. Firstly, it's a very bad at CAD. CAD is quite complicated, and since we have a combination of physical and conceptual parts that we need to 3D print, it's hard to fit them together. The motor, which is already here, and so we did not have to model, is hard to fit with the different 3D modeled pieces that we made. This means that we had a lot of broken and unworkable 3D prints, as you can see in the 3D print graveyard. Furthermore, we noticed that the field of view of the Raspberry Pi is tied to the resolution. This means that we need the highest resolution of the Raspberry Pi video in order to see the whole range of what this camera can see. This gives us a lot of different challenges along the way. Furthermore, the IR sensors that sense the edge of the table and the front and any obstacles in front of it are very unreliable. Sometimes they flicker, and such flickering can lead the code to go askew.
So a few more of the hardware challenges we encountered. One of them was laser cutting this beautiful tower, as you can see. We had a lot of issues with that, with the laser not cutting all the way through the wood and doing many passes and whatnot. So that was a bit of a mess. Also, doing the glue up was very difficult because you have to apply the glue to the edges and then hold it in the shape it needs to be in, which is not an easy thing to clamp. Another issue we had, in our original design, we had the motors mounted in the middle of the chassis and axles extending to either side to make sure that the left and right sides would move at the same speed. That was the idea anyway, but in practice that part was way too hard to 3D print and to fit properly. And also it had to be very thin, and that made it very weak, so we had a lot of them snap as well. Another issue was with our H-bridge. We were not familiar with the way that the Raspberry Pi was supposed to talk to the H-bridge, so we had a lot of difficulty getting them to communicate properly, or at least in the way that we expected. And then we also had some issues powering the H-bridge, because it has a 5-volt and a non-5 volt power input, and they do different things based on if a certain jumper is connected or disconnected. So we had to learn how the H-bridge works, and then tell the Pi how to talk to the H-bridge, and then power the H-bridge properly. So that took us a while as well.
Now I'll go to the software aspect of our project. Computer vision is applying machine learning to images. Machine learning is using a family of algorithms that learn through training process, which they slowly adjust themselves to fit large data sets. In our application, that means that the program should identify notebooks versus non-notebooks. Non-notebooks being back of desks, iPads, and anything that doesn't include notebooks. Formally, what you would call this project supervised computer vision neural network with both convoluted and fully connected layers.
Okay, so what are convolutional and fully connected, or otherwise called dense layers? Well, convolutional layers in a network, what they do is they group chunks of the image into larger chunks. And that allows the program to more easily be able to recognize features, such as the edge of a notebook, or in our case, what we were expecting it to train to is the spiral bind, because this is a very recognizable feature for a neural network. And these dense layers are a little more simple. They are just large matrices. And so as the network goes through dense layers, it's just doing a large amount of matrix multiplication. So for our training, we needed a large and diverse data set. We needed a big computer, and we needed a lot of time. So in this data set, it actually contained over 4,000 images for our most recent version. And after pre-processing, we actually turned that into over 9,000 images. So we do some image duplicating with a flipping operation. We started simple, trying to just recognize this exact notebook. And then as the dataset grew, we allowed more complexity, like for instance, a notebook with a spiral bind and white pages. We developed techniques for processing these large amounts of data. We had an entire software pipeline whereby which we could take a bunch of images really quickly, upload them all, pre-process them all in a batch, and then put them in the training location. And I've mentioned pre-processing a couple of times. What that is we're doing a few operations to the image that make it easier for the network to deal with. So we're grayscaling, and we're drastically lowering the resolution, and we're also rotating. And all of those techniques are to make it easier for the network to recognize the features that are important and ignore the features that aren't important, and also to reduce computation time.
We initially thought that the hardest part of this project would be the neural network setup. However, we quickly learned that the problem would be actually the data set. We tried at first to have all notebooks be part of the data set. Spiral bound, non-spiral bound, just paper, textbooks, everything. However, we noticed that this would made a very inefficient neural network because it would identify different loose white things as paper as well. Furthermore, we noticed that we needed to take a bunch of pictures because it would very quickly overfit. And to account for this, we did burst shots where we would slowly rotate and move as if we were the light camera. And because of that, we had a lot more pictures in a much shorter amount of time. To go into specifics of the neural net itself, to account for overfitting, as I mentioned previously, we did a couple of things. We added weight decay for the actual network. We added 50% dropout, and where 50% of the weights for each iteration of the training, they're lost, they're zeroed, so that the program does not learn to just match each weight with each image of the training data set. Furthermore, we also included different batch normalizations and convolutional layers. The convolutional layers were 3x3 kernels, which means that it takes 3 pixels together and clumps them, as Leo mentioned previously. And then we also had dense layers. To be specific, our best model had 5 dense layers and 3 convolutional layers.
As a last note about the software, it's worth mentioning we have 17 million trainable parameters, and our model size is 70 megabytes. So not a huge model, but fairly sizable. So okay, now we've heard about the software, we've heard about the hardware, so let's play with the model a little bit and see what the performance is like right now.
Here are some working examples of this lamp being used. This works as usual with just a blank notebook. And it works when someone is writing on it. However, it also works with different lined paper, such as this lined notebook. However, note that it needs to be a spiral bound. It works on the other side as well, when flipped horizontally. And it also works when it's flipped with just half a page seen.
So as Dima just demonstrated, the model is far from perfect. It recognizes a lot of objects that are not notebooks at all. So let's see. Yeah, so it's recognized the back of this breadboard as a notebook. And also, we didn't show before, but many examples of objects that are not notebooks are not recognized. And this includes, in large part because it was a large part of our data set, tablets. It's very good at rejecting tablets. So here I have some more objects laying around. You can put all these things and no notebooks for most of these objects. So by far the most amusing example we found is that a tablet, of course, can display a notebook, which is very confusing for our notebook recognizing robot.